Okay, we're continuing on here, talking about types of reactions. And last time, again, we really were focusing on, as we talked about in lab yesterday, and we did some of that stuff, the double displacement reactions. And as I mentioned, really, it is sort of the big classification of reactions, which more sort of specific classifications sort of fall under our double displacement reactions. And these are precipitation reactions, where some type of precipitate or solid is made. Also, as we'll talk about today, acid-base reactions, and that is really where water is made. And again, these are really two of the three reasons why a reaction takes place, is that formation of a solid or really the formation of water. And again, the way you can recognize these type of reactions is pretty straightforward. You always will be starting with really two ionic compounds, and always in that situation is always the positive guys, as we've talked about, will switch partners, again forming new ionic compounds on the other side. And in one case, obviously, could make a solid, could make a water or liquid there. And again, that is basically how you know it's going to be a double displacement reaction. Later on in this chapter here, we will talk about redox reactions, which really account for the other reason why a reaction takes place, which is, again, sort of electron transfer sort of happening. Now, we talked about the molecular equation, where we do, again, write everything out with the proper formulas. We also have our total ionic equation. And we have our net ionic equation, which is really the equation that describes sort of what is really taking place when you do a particular reaction. There's also spectator ions along the way. So I think we've done this one a couple of times, but again, the steps to sort of getting to that net ionic equation, you want to start with a balanced molecular equation. So this example here, where we have something like silver nitrate, and reacts with our sodium chloride. And once again, we know that we have a double displacement reaction because of the two ionic compounds. We also know, again, that we're going to switch partners. Once again, you want to always make sure, if you are predicting what's on the other side of the arrow, that you just get the right formulas down first, regardless of the balancing of the equation. And you don't want to do those two things together, which is a very, very common mistake that people make, is they try to balance and also write the formulas on the other side. So by just doing the formulas first, we should get silver chloride that looks like this, and that's because silver is +1 and chloride is -1. And we should get sodium nitrate, which is something that looks like this. And again, sodium is +1 and nitrate here is -1. We could use the solubility rules, which is something else that we talked about last time, to help us determine whether or not these things will be soluble or insoluble. And if something is soluble based on solubility rules, they will get the aqueous symbol next to it. And that basically means that it's a solution. So when we have something that has nitrate in, as we talked about, that definitely is soluble in everything. There's no exceptions. So we know for sure that that's going to be aqueous. Also, chloride, as we talked about a number of times, along with bromide and iodides, they are soluble in everything except for really three things, which is silver, lead, and mercury. And none of that is in this case. We also know, by the way, again, the sodium, which is group 1, is soluble in everything as well. So as soon as you sort of get one of those guys in a formula, that's, for example, soluble in everything, there's no exceptions, you don't really need to look any further than that. You will know that it's going to be aqueous. Here, though, we do see the chloride, but it is hooked up again with one of the exceptions. So that is going to mean that's going to be opposite of normally being soluble, which means it will be insoluble, and that will mean that a solid would form. And lastly, here we have our sodium, which is soluble in everything, along with our nitrate, which is soluble in everything. So we do know that this is aqueous. So again, we can definitely use our solubility rules to help us determine sort of what thing might be the solid if you're not sure of. Again, this would be the molecular equation. We would want to make sure it's balanced, which it is in this case. Anything that is a strong electrolyte will break apart in solution. So really, when you dump those things into, say, a beaker, you really get silver ions floating around, you get nitrate ions floating around, you get sodium ions, and you get chloride ions basically floating around. And we can write an equation that basically sort of describes what's happening in that sort of solution. We do know from our solubility rules, though, that these two guys are going to come together, but everything else will be floating around at that point, which would mean silver and the nitrate there would break apart. We would have our sodium chloride also break apart. Our silver chloride will stay together again, otherwise it would not be a solid. And then we have our sodium and our nitrate basically falling apart. And again, that is our total ionic equation. That is obviously our molecular equation there. And in this equation, it really does sort of describe what's happening when you kind of put it into, say, a beaker or a test tube. You got all those ions flying around. We got the silver and the chloride coming together as a solid. And we can look at this and again find our spectator ions, which are the same ions looking exactly the same on both sides. And they should look exactly the same on both sides. They also should have the same number of ions on both sides if you did everything correctly in terms of balancing the equation. So as we talked about, I think last time, you get to this step and you got like 2 ions on one side, only 1 on the other side, you probably didn't balance it right or don't have the right formula somewhere along the way. These are our spectator ions, which again, basically get canceled out because they're really not leading to the product being formed. And what we are left with is ultimately what is occurring in this reaction. Really, the reason why this reaction takes place is this formation of the solid here. And that is our net ionic equation when we do that. Any questions on any of that stuff there that we talked about a couple of times already? Pass that around. Okay, so let's continue on and look at maybe a couple more examples here of this type of reactions. So why don't you give this one a go? Write the balanced molecular equation, the total ionic equation, and the net ionic equation, and ID some spectator ions here for this one. So we got a reaction of potassium carbonate and nickel 2 chloride. So see what you come up with here. Okay, let's take a look to see how we're doing. So we want to write an equation between the reaction of potassium carbonate. So remember, you want to start out with the right formulas. Potassium is +1, carbonate is CO3 2-. So a little bit of that there is what we should be looking for. Nickel 2 chloride means the nickel has a +2 charge, chloride has a -1 charge. So the correct formula again should look something like that. Now, if we're not sure what type of reaction, we should be able to recognize that it is a 2 ionic compound. So we've got a positive, negative, positive, negative. So once again here, we're going to swap partners in this case. And we do want to start with, again, the correct formula, not necessarily balancing at this point. That means when I take the potassium and I take the chloride, it is +1 and -1, which gives me the proper formula of KCl, not K2Cl2, because that is incorrect. Also, when I put it together there with the nickel, which has a +2 charge, and our carbonate, which has a -2 charge, I should end up with something that looks like this. So again, you want to make sure you get the proper formula down first, and now you can look at whether or not it is balanced, which it is not in this case. So I think we do need a couple of numbers. I believe we might need a 2 right about there, and that might be all the numbers we need. Now we do have it balanced. We could also look at our solubility sort of rules to help us decide sort of what is going on here. Obviously, these guys are aqueous solutions because it kind of says that in the actual problem. But regardless of that, when we look at the first one, we see potassium, which is soluble in everything because it's group 1. So we don't need to look any further. We once again here see chloride on this guy, which is soluble in everything except for silver, lead, and mercury, which means this guy also would be aqueous. Coming here, we have potassium, which is soluble in everything. So that is aqueous. And in this case, our carbonate is going to be insoluble, as carbonates are mostly insoluble except for group 1 and ammonium. So that is how we can use our solubility rules that we talked about last time to determine which one is insoluble. Any questions on that there? Now that we have this, we could write our total ionic equation, as obviously this is our molecular equation here. So our total ionic equation, again, we're going to break apart everything that is pretty much a strong electrolyte. Anything that is a weak electrolyte should stay together. Anything obviously is a solid, a liquid, even a gas usually should all stay together. But if most of the things are strong electrolytes, they should completely break apart. So breaking this guy apart, which it will, that 2 for the potassium goes in front when we do that. And our carbonate, there's just one of them. Our nickel 2 chloride will also break apart into a nickel with a +2 charge. And once again, for the chloride there, our 2 comes to the front. And again, it is not Cl2 minus or anything like that. Again, it's 2 Cl minuses that are floating around in that solution. Coming to the other side, our 2 that's in front of the KCl will get distributed to everybody behind it. And again, this is how we get everybody with the right numbers. And obviously our solid here will stay together because it is a solid. This is our total ionic equation in this case. And here we will look for our spectator ions. So we got a couple of potassiums on each side. We also have a couple of chlorides that look exactly the same on each side. And as you can see, we also have the same amount of those ions on each side, which is important. Those guys are going to be our spectator ions, which means we will cancel them out. And it's going to leave us our overall net ionic equation, that what is really happening here is the nickel is going to find the carbonate. And it's going to form that solid nickel 2 carbonate in this case, which would be our net ionic equation in this particular example. Any questions on any of those things? I think I mentioned a number of times, but number hurts one more time. Molecular equations should not have ions and charges. Total ionic and net ionic, they have ionic in the name, which means those guys that are ions should have charges. And you should also include the states, obviously, as you go through those. Any questions on that particular one there? Okay. All right, so why don't you try these 2 as well? Why don't you let's do all 3 again. It's good practice. Let's do our balanced molecular, our total ionic, and our net ionic equation for each of these. So look, so once again, looking at this, we know it's a double displacement reaction, as we do see obviously 2 ionic compounds. So again, we're going to switch our partners here and then get the right formula. So K is K plus and nitrate is NO3 minus, which means we just need one of each of those. And on the other side there, we have silver, which is always +1, and chloride is -1, which means, again, when we put it together, we get our silver chloride in this case. Looking on the right-hand side here, we have potassium, which is soluble in everything, so definitely will be aqueous. And this is our silver with our chloride that we've seen a number of times, which means it's going to be insoluble, as that's an exception there for chloride. We want to make sure it's balanced, and in this case, it is balanced. If we were going to our total ionic equation here, we would break apart our potassium chloride into its ions. Same thing with our silver nitrate, as it's a strong electrolyte. Our potassium nitrate will also break apart. And once again, our solid will stay together, much like a liquid or a weak electrolyte if we have. In this case, this would be our total ionic equation here. Looking for our spectator ions, it's going to be the potassium and the, not chloride, but the nitrate there would be a better circle, I think. Get rid of that box. There we go. So again, looking on both sides, we do see, again, potassium and the nitrate looking exactly the same. That being our spectator ions will get canceled out. leaving us our, once again, in this reaction, the same net ionic equation we saw before, our silver really coming together with our chloride to form our solid in this case. Any questions on that one there? And obviously this would be our net ionic equation here. Looking at the last one here, also ionic on this guy and this guy, which again tells us it's a double displacement reaction. Once again, putting this together here gets us a sodium with a +1 charge and a chloride with a -1 charge, giving us again NaCl. And in this case, our calcium is +2 and our sulfide is -2, which means we end up with that as the correct formulas. Here we do need to do a little balancing, so what do we need there? A 2 right there. We'll do that. Looking at our solubility rules, sodium involved here, which means it is soluble in everything. We also have sulfide here, which is insoluble in everything, except for a few exceptions, and calcium actually is one of those exceptions, which means that actually will be aqueous as well. So this would be our molecular equation in this case. If we got to our total ionic equation, we would have something like this, Na2 sodiums, as that 2 would come in front. Our sulfide would break apart. Our calcium here would break apart. The 2 for the chloride also comes in front when you break it apart. The 2 in front of the sodium chloride gets distributed to everybody behind it, and 2 chlorides there. And our calcium sulfide also going to break apart in this case with a calcium ion. And if I could squeeze it in down here, a sulfide ion there. That means that this would be our total ionic equation. That means the spectator ions in this case is everything. Yes. So basically in this deal, you got all the ions still floating around. Basically, nobody is coming together to make any type of solid or water, which means really you get no reaction in this case, right? Because everybody pretty much cancels each other out. Everybody's still going for a swim, basically. Yeah. Any questions on that one there? All right, so again, it sometimes happens, and obviously this would be much like what you did yesterday, and with some of those ones where you put them together and you did not see a solid form. Basically, all the ions are still floating around, basically in the solution part, and nobody's coming together to make a solid. Any questions on those two? All right, one last one here, and we'll wrap it up for this type of reaction here, or in a sense, right? The equation for what you get here when we take ammonium sulfate and lead-2 acetate together. And why not one more time, all three of them equations. Okay, let's take a look. So we're starting with ammonium sulfate. We're mixing it with lead-2 acetate. Again, this is a positive negative guy, positive negative. So we want to rearrange these guys correctly. So we're going to put ammonium with acetate, which actually will give us NH4C2H3O2. Again, that's another way to write acetate. I think we talked about it the other day. We're all going to put our lead, which has a +2 charge in this case, together with our sulfate that has a -2 charge. And that should give us something that looks like that there. Now, again, that we got the correct formulas down, we want to then balance it. In this case, it looks like perhaps a little polyatomic ion balancing, a 2 there. And that actually, I think, will take care of everybody that needs to be. We can look at our solubility rules here to help us decide. And again, we know the first 2 are aqueous. Really, because it told us, but also ammonium and acetate, there's both tells us it's going to be aqueous. Here, ammonium is soluble in everything, so that would be aqueous. Sulfate will be insoluble in this case based on solubility rules, so that will be our solid that is formed, and that should be our balanced molecular equation here. Any questions on that one there? So again, I can't stress enough how important it is to get the right formulas first and then balance. We're gonna go to our total ionic equation here. Once again, this 2 gets moved in front as we go to break it apart. So we will have 2 of the NH4 pluses. We will have 1 sulfate. Our lead 2 acetate will also break apart. Once again, lead here will have a +2 charge. And this 2 does go in front of the acetate here when we do break it apart. And the acetate has a -1 charge. Coming to this side, our ammonium, the 2 will get distributed to both of the guys behind it. So that's going to be 2 of the NH4 plus and 2 of our acetates as well. And once again, here our solid, I'm going to go underneath, will stay together here. And that is our total ionic equation. Any questions on that one there? And again, here we're going to be looking for our spectator ions. So we got 2 ammoniums on both sides. We also got 2 acetates there on both sides. So these are our spectator ions in the boxes. We will cancel those guys out, leaving us our net ionic equation here, which is, again, our lead going to find our sulfate and going to make that solid lead 2 sulfate in this case. Questions on any part of that there? All right, so these again, double displacement reactions. More specifically, what we've been talking about here up to this point really is more of the precipitation reaction that occurs. And again, that takes care of the sort of solid that is formed as a result of why a reaction takes place. Now, another type of double displacement reaction that does occur is an acid-base reaction. And in an acid-base reaction, it does take care of the formation of water. So as we talked about, I think previously, in a precipitation reaction, which is a double displacement reaction, you could usually see the solid being formed. Sometimes, obviously, when you do this sort of acid-base reaction and you form water, you can't necessarily see it, perhaps, that you made water. But water being formed, again, is a second reason why a reaction takes place. And this definitely occurs in our acid-base reactions. Sometimes these are referred to as acid-base neutralization reactions. What makes something an acid is the ability to produce H+ ions in solution, which are sometimes referred to as protons. That free H+ are sometimes also referred to as hydronium ion, which is H3O+. They're basically the same in acid-base chemistry. So as you'll learn, if you take 200B, pretty much these guys are basically the same thing. It represents basically sort of the acid part of the solution. Now, bases, on the other hand, they are able to form hydroxide ions in solution. And that's really sort of the important part of this type of reaction is when you take an acid and a base, pretty much your acid is going to supply the H+, and your base, for the most part, is going to supply the OH-. And it is those two guys that come together to basically make the water. So the acid is usually the one that provides the H+ for the water. The base provides the OH-, and those guys coming together will make that water in this reaction. Now, when we do react an acid with a base, pretty much you usually will always get 2 things, as it shows there on the bottom. You will get a salt and you will get water. So as we just talked about there, the water coming from the H+ from the acid, OH- from the base. A salt is just a fancy word. I don't know how fancy it is, but it's a fancy word for an ionic compound. So it's basically an ionic compound, a cation, anion together, basically coming together is what a salt. So you always get that. And really the salt is made from the other parts of the acid and base coming together. So the acid and base that's not used to make water, those two guys come together to make the salt, which is the ionic compound in this particular case. Now, in these reactions of acid and bases, I think we talked about it previously, but just to reiterate, there are certain acids that are considered strong acids, and here's a list of some of them. Some strong acids for sure, which are on this list here: hydrochloric acid, hydrobromic acid, hydriodic acid, perchloric acid, nitric acid, and sulfuric acid. So pretty much those four acids, as we might talk about when we talk about naming, are really strong acids. They're also strong electrolytes, which means when you have them in a reaction, they will 100% break apart. Pretty safe bet, as I might have mentioned earlier, that if you have an acid and it's not one of those six, it's probably going to be more so a weak acid. And what that would mean is that it is a weak electrolyte. And when you would get to like a total ionic equation, you would actually keep it together and not break it apart. So again, that's sort of the importance of what we've been talking about here. So as you can see there, dropping down things like hypochlorous, carbonic acid, hydrofluoric acid, these are some weak acids. And again, the list of 6 strong acids is a good one to know as you go through chemistry. You know, pretty much that kind of helps you decide whether or not it's going to be strong or weak. Now, bases as well. A lot of strong bases have hydroxide in the actual formula, like we see here. Some strong bases like sodium hydroxide, potassium hydroxide, calcium hydroxide. Pretty much if you go to the periodic table in group 1, you got like lithium, and then you got like sodium and like a potassium, then you come over to calcium. If you kind of go this way, any of those guys in group 1 or group 2 that have hydroxide with them is pretty much going to be strong bases in most cases. Most of those guys coming down the potassium, hanging right to calcium, coming down are going to really be considered strong bases. Again, group 1 is the alkali metals, group 2 is the alkaline earth metals, and the word alkaline means basic. So that's where a lot of our strong bases come from. Not all bases will have hydroxide in the formula. Some weak bases are able to produce hydroxide in solution, which is why they're still considered a base. And ammonia is an example of that. So if you look at something like ammonia, it does not have OH in it, but when it does react with something like water, what happens is it will actually pick off an H plus from water, and it will make NH4 plus, and I'll go over here, OH minus, and it has the ability there to produce OH minus in solution, which is why it's considered a base. Also why a lot of times in labs, if you need ammonia, they give you ammonium hydroxide, which is basically the aqueous version of ammonia. It is a weak electrolyte and a weak base, and that's those 2 arrows that we talked about. When we talked about weak electrolytes, it will set up an equilibrium. But something like ammonia, which is a weak base, it does not have hydroxide in it, but it's able to produce hydroxide, which means it's still a base. Any questions on that? So in this neutralization reaction here, we have our hydrochloric acid, which is a strong acid. We have our sodium hydroxide, which is a strong base. And really, although it is an acid-base reaction, this is still a double displacement reaction. This is a positive negative guy, a positive negative. And once again, these guys are going to switch partners. So again, although it's acid-base, it does fall under the umbrella of double displacement reactions. And once again, on the other side there, the H plus and OH minus, that is what's going to make our water. Again, from the H plus from the acid, the OH minus from the base. And what's left over is pretty much our sodium and our chloride, which will come together here to make our salt, which is our ionic compound in this particular case. If we were going to our total ionic equation here, we would have H plus and Cl minus, which is a strong acid. We have our sodium will break apart, and our hydroxide, which is a strong base. Our sodium chloride here will also break apart into a sodium ion and a chloride ion. And here water, which is a pure liquid, will stay together. So again, we will not break apart water in this particular case. In this case, if we look at it, our spectator ions is our chloride and our sodium. That's our spectator ions. When we cancel them out, we get pretty much the net ionic equation that occurs whenever you take a strong acid with a strong base, which is basically the formation here of water. And again, that is one of the three reasons why a reaction takes place, is basically water being formed. You could put together any combination of strong acid, strong base, and that is always where you will end up. Hey, if you took like nitric acid, which I don't know if I put on my list, but nitric acid is a strong acid, plus a potassium hydroxide here. Once again, we will have a double displacement reaction. We will make the water, and we will make our salt, which is our K plus and NO3 minus, and that is going to be aqueous. Breaking this guy apart, H plus and nitrate, which is a strong acid, will break apart. Our potassium hydroxide, which is a strong base, will also break apart. Our water will stay together. Our potassium nitrate will break apart. And in this particular case here, it is going to be our nitrate and our potassium that are going to be our spectator ions, so they will cancel out, leaving us with the same net ionic equation. So always strong acid, strong base. Pretty much what is happening is the formation of water, which again is why it's referred to as a neutralization reaction. And again, really the second reason why a reaction takes place. Again, if you threw these guys together, you probably wouldn't be able to see like, hey, I made water, but that is essentially what is going on in this particular reaction. Any questions on that there? I did put nitric, that's good. I remembered. All right, acid-base reactions fall really under the big umbrella double displacement reactions. Again, it's the formation of water basically is what's happening in that reaction. All right, and that's what we see here. Now, another sort of result that can occur in a double displacement reaction is actually you can form a gas, and a gas can be generated in addition to obviously water or a solid, but a gas forming reaction can occur in a double displacement situation. And there's really kind of two ways that a gas can sort of be generated in this type of reaction. One way is directly, so just directly swapping out the sort of ions there, you generate something that is a gas. The second way is actually a secondary reaction that occurs after the sort of switch of ions. You get sort of a substance that's formed that will very quickly sort of break apart into a gas. So it's kind of an indirect formation of a gas, and the other one is directly just straight up get a gas. So if we were to take our potassium sulfide here, which is our positive negative guy, and our sulfuric acid, which is positive negative, also a strong acid or sulfuric acid, it will switch out and make potassium sulfate and hydrogen sulfide gas. So directly out of this sort of switch of ions, we will generate hydrogen sulfide gas, which you really don't want to generate, get a smell, but it will make this gas directly here. Now, in the case, if we took potassium sulfite and swapped it in there with our sulfuric acid, we will actually get K2SO4, which is our potassium sulfate. And in this case, though, we will get sulfurous acid. So sulfurous acid here, weak acid. It will actually then go through a secondary reaction, which is known as a decomposition reaction. And a decomposition reaction, what that means is it'll essentially just break apart, basically. And when it goes to break apart, that sulfurous acid will break apart into water and SO2 gas, which again is our secondary sort of product that is made here. You may be familiar with this sort of reaction or not realize that you're familiar with it. If you took any type of acid, for example, and maybe you got some heartburn, and maybe you take some sodium bicarbonate, for example, and you do a little reaction here, you'll get a little sodium chloride, and you'll get some carbonic acid. So again here, carbonic acid, also a weak acid. That carbonic acid will very, very quickly, almost instantaneously break apart into water and CO2 gas, which is like the plop, plop, fizz, fizz bubbling that you see when you put those things together. So that happens a lot and it's our double displacement reactions, we get a product here. A lot of times it's some type of weak acid. Sometimes we'll break apart and sort of go through a decomposition reaction secondarily to the double displacement reaction and form that gas. Any questions on that there? All right. So here's a table that sort of summarizes some of the decomposition that occurs if you have a metal with sulfide or a metal and HS, and it's reacting with an acid. You will generate that hydrogen sulfide gas directly, no decomposition occurring. Again, any of those guys with like carbonate or sulfite reacting with an acid will make one of those acids that will kind of go through that secondary decomposition that we just saw on the previous page, make either CO2 or SO2 gas. And ammonium with a base will make ammonium hydroxide, and you'll make ammonia pretty much as a result of that in that reaction. So if you take a base and ammonium involved, that will generate out ammonia, because basically what's going to happen is this guy's going to give away his H plus, and it's going to leave that as NH3, and it's going to release it as a gas in that particular case. So another sort of outcome of a double displacement reaction is you may not necessarily maybe form a solid or a liquid, but the ultimate result may end up being, in addition, a gas that is formed. Any questions on double displacement reactions here? Okay, so double displacement reactions, as I mentioned, is that big classification where, as we've seen, more specifically, precipitation reactions and acid-base reactions basically fall underneath as a more specific classification. Again, as we talked about, our solid and our water being formed as a result of it. Now we're going to talk about, for the rest of this chapter, really the other big classification of reactions, which are redox reactions. And redox reactions basically account for everything else that basically occurs, and they account for basically electron transfers. So let's talk a little bit about those. Maybe there we go. So redox reactions, which is what these guys are sometimes sort of referred to, means oxidation reduction reactions, and they account for really the third reason why a reaction takes place, which is an electron transfer. And underneath sort of the big umbrella of redox reactions sort of fall all the other ones that you may be familiar with. You have your synthesis reactions that fall under here. You have your decomposition reactions. You have your single replacement. You have your combustion reactions. So, you know, for the most part, everything that's not a double displacement reaction will fall sort of underneath the redox sort of umbrella. So redox means oxidation and reduction, and really there is a few definitions of those things. So let's just take a look at it here. Maybe when we talk about oxidation, there is really the definition that most of us use here in general chemistry, which is, it means that it is a loss of electrons. So something that loses electrons. And when we talk about reduction, it really is a gaining of electrons. So sometimes people like to remember this as Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. Put them together, put Leo the lion on the oil rig, he goes grr. You don't have to choose. You could just remember everything there. That would be good. Now, I will say that there are a couple of other definitions of oxidation and reduction that we really don't use too much in general chemistry, but you definitely do use later on if you do take organic chemistry. So another oxidation sort of definition is the gaining of oxygen from reactants to products. So some substance gains oxygen as it goes from left to right on the reaction. And also the losing of hydrogen, or H2, as you go from reactants to products, is another sort of definition of oxidation. For reduction, it's kind of the opposite. It is losing oxygen as you go from reactants to products, and gaining H2 as you go from reactants to products. So those definitions of hydrogen and oxygen a lot of times are used in organic chemistry, where it's much easier to follow oxygen and hydrogen being added or lost, rather than looking at things like charges and oxidation states, because there's not a lot of metals that kind of occur there in organic chemistry. So I would say in here, and most of the time, it is these two definitions that we really do sort of follow when we are looking at oxidation and reduction. So when something gets oxidized or when something gets reduced, you really follow, as we'll talk about, what is known as the oxidation state or oxidation number, which is a little bit different than the charge. And you look at how it changes as you go from reactants to products. So there's a really super simple way to figure out whether or not something is being oxidized or reduced. You could use actually just a good old-fashioned number line type of deal, where positive numbers are there and negative numbers are there. And when something loses electrons, does it become more positive or more negative? It does become more positive, right? Because it lost electrons, it loses more negatives, got more protons, so it becomes more positive. So if you see somebody's oxidation state or number start moving in this direction on the number line, kind of in the positive direction or towards the positive direction, doesn't necessarily have to get positive, but just kind of moving to the right, that thing is going through oxidation. Now, when somebody gains electrons, they actually have more negatives than positives, so they become more negative along the way. So if you follow the oxidation state and it's kind of moving towards the left on the number line, are becoming more negative, that guy is going through reduction. So it makes it like really sort of an easy way to follow, you know, if something's being oxidized or reduced. So for example, if I had something like this, we'll just do just these two guys. So what is happening here in terms of the iron? The iron in the first case is iron with a +3 charge, right? Iron in the second case is an iron with a +2 charge in this case. Is iron being oxidized or reduced? Iron is being reduced in this case. It is starting at +3, which would be like here, and it's ending at +2, right? Which means it is moving to the left there, becoming more negative. And that means that this guy is going through reduction. Yeah. So that is really the way that you could use that number line. Is like super simple. It'll always give you the right answer as long as you can count, I suppose, and we'll know which way left and right is. You'll be okay in that particular case. One of the other sort of nice things about an oxidation reduction reaction or a redox reaction is they always occur together. So if there is something being oxidized, there should be something being reduced. So the good news is if you could just figure out one of the things, the other guy is doing the opposite. So that's kind of the nice thing about it. You could kind of figure out what's going on with somebody else by just what's happening with the other substance that is present. Any questions on that there? All right, so if we look at this reaction here, this is an overall reaction. And this overall reaction is really magnesium plus oxygen, making magnesium oxide. And in this particular reaction, this is really a redox reaction that's occurring. And if we look at really sort of the oxidation states here of magnesium in the overall reaction, that is 0. It is by itself a reminder that anything that is uncombined by itself has a 0, no charge, and really has 0 oxidation state. Oxygen, that is naturally how it comes, which means it also has a 0 oxidation state. It is only really when things get together that they sort of get those sort of states. And in this case, this is an ionic compound, which means magnesium is +2, oxygen is -2 in this particular case. So again, if you weren't sure what's going on, you could use our little number line approach here. And if we look at the magnesium, it starts at 0 and it ends at +2, right? which means it is becoming more positive and it is going through oxidation. And by default, that means that the oxygen is going through reduction, but we could also do it for the oxygen. The O2 on the left-hand side starting at 0, and the oxygen on the right-hand side there becomes -2, which means it's becoming more negative. And it is going through reduction. So again, we could use our little number line approach there to figure out what is happening in each of these cases. We can write two half reactions to describe what's going on, and this is what is known as the oxidation half reaction and the reduction half reaction. And in this case, it is our magnesium going from 0 to +2 here. And in an oxidation half reaction, electrons are always found on the product side because they are like being given off, being lost. So they are on the product side there. In this case, we actually have 4 electrons because each magnesium is losing 2 electrons, and there's 2 total magnesiums, right? That's 4. That's how we get the 4. By the way, a balanced half reaction should be balanced like a normal equation. That means that you have 2 magnesiums on both sides. Overall charge is 0 here, +4, and -4 from the electrons is 0. So everything is balanced in that half reaction. So when you look at that half reaction, like I said, they've got 2 magnesiums on each side. Overall charge is 0. Overall charge on this side is 0 as well. Again, 2 magnesiums at +2 is +4. And 4 electrons is -4, so it is 0. When we have the reduction half reaction, because they are gaining electrons, electrons will always be on the reactant side in the reduction half reaction. And in this case, the oxygen here is going to pick up those 4 electrons from the magnesiums, and you're going to end up with our 2 oxygens that have a -2 charge. Same thing here, we have 2 oxygens on both sides. Overall charge here is -4. Overall charge on this side is -4, and that is balanced as well. It doesn't have to be 0 on both sides, it just need to be the same charge on both sides when you look at a redox reaction. They are called half reactions because, as you can see there, if you add them together, you get the overall reaction that is taking place. So if we look at this here, if we take our magnesiums and our oxygens, and again our oxidation and our reduction half reaction, when we add these together, and when you have basic sort of simple redox reactions like these two here, half reactions, there's one thing that you have to make sure is the same in both reactions before you add them together, and that is the electron. So the electron should always be the same number of electrons in each of the half reactions before you add them together. And that's because it is an electron transfer, which means whoever is losing electrons, somebody else should gain those exact same number of electrons. So it should always be the same number. And when it is not the same numbers, you do need to multiply perhaps the half reaction by a number to get them to the same. You may have to multiply both half reactions by a number to get the electrons to the same. Electrons should always be the same number in each half reaction. You also see, if you do it correctly, electrons are on opposite sides of the arrow. They should never ever be on the same side of the arrow if you want to do this correctly. Yeah, so they should always be on opposite sides of the arrow, which means you should have an oxidation and you should have a reduction reaction that's taking place. So when we add them together, basically what happens is anything that's on opposite sides of the arrow that is the same can either completely cancel out or reduce down. Kind of like you're subtracting. You can think of the arrow like an equal sign, like in math, you're kind of like subtracting it from one side to the next. So in this case, because our electrons should always be the same, they will completely cancel out as they're on opposite sides of the arrow and the same. At this point, anything that's on the left-hand side of the arrow will stay there. Anything on the right-hand side of the arrow will stay there. So on the left-hand side of the arrow, we got a couple of these guys plus this. On the right-hand side of the arrow, we got this guy and this guy. These are 2 ions which will come together to make our magnesium oxide in this case here. Any questions on that? So these half reactions basically show half of the overall redox reaction that's taking place. And when you add them together, you always want to make sure that your electrons do cancel out. So redox reactions happen a lot, and you take 200B, you'll have a whole chapter on electrochemistry, which is pretty much all these type of reactions that take place. And for the most part, a good thing to remember is in terms of redox reactions is anything that is an ion that basically has a charge is floating around in a solution free. Anything that pretty much is a solid, has no charge, is going to basically come out of solution. So if you have some electrodes here, basically what happened is all this solid zinc is going to go out into the solution as zinc 2+, and then the copper that's in that solution will jump out of the solution and plate it on. Hence the kind of coloring that you see there on the metal. It's all that kind of copper jumping out of solution and going onto the metal, basically because it's becoming solid. So anything with a sort of charge that's an ion is floating around in the solution. And obviously anything that's a solid is not floating around in the solution. We'll probably attach to the metal if there's a metal piece there, or it may just end up on the bottom. So if we look at this reaction here, which is our zinc plus our copper 2 sulfate, this is also a redox reaction. Our zinc here by itself has really no oxidation state. This is copper 2 sulfate, which means their copper here is +2, and really our sulfate altogether there is -2. On the right-hand side, our zinc now will have a charge of +2, our sulfate will be -2, and our copper here will have no charge or oxidation number. Now, in this case, what is being oxidized? So we could use our number line here to help us figure it out. If we look at the zinc to start with, zinc is starting at 0. And it is ending on the right-hand side at +2, which means it is becoming more positive, which means it is going through oxidation in this case. If we look at the copper on the left-hand side, it actually has a +2 charge, which means it would be like here. And on the right-hand side, it ends up with a 0 oxidation state, which means it is moving in the left direction there, becoming more negative, and it is going through reduction in this case. Any questions on how to use that there? What about the sulfate? Is it changing? It is not changing, right? The sulfate's just hanging out, having a good time. Maybe, maybe not. So we could actually, if we wanted to, write a net ionic equation that's happening in this type of reaction. By the way, this type of reaction is a single replacement reaction. Is really what's happening, and it is a redox reaction. So if we were to write sort of our total ionic equation in this case, we have our zinc. This guy would break apart. Our zinc sulfate would also break apart. And obviously here, our solid copper would stay together. In this case, we could see why sulfate is not changing. It is actually just a spectator ion in this case. Yeah, so this is actually our spectator ion. Which, just like we did before, we could actually cancel it out, and we would be left with a net ionic equation, which really shows the redox reaction that is taking place here. So this is our net ionic equation. That is our total ionic equation there. And it is our zinc that's going from 0 to +2 being oxidized. And those electrons are heading over to the copper that has a +2 charge, and they're going to pick up those electrons and become copper with really no charge there, oxidation state, as they gain the electron. So this is, again, the third reason why it happens. It is really an electron transfer that is happening there between the two in this particular case. Any question on that? So you can write actually a net ionic equation for a single replacement reaction like this. You just actually end up with only one spectator ion rather than two in this particular case. Now we could write our really reactions that are taking place here. So really our oxidation reaction is our zinc going to our zinc with a 2+ charge and a couple of electrons coming off. That is our oxidation half reaction. Our copper is going to pick up those 2 electrons and make our copper here, and this is our reduction half reaction. Now, when we have something that is being oxidized and something that is being reduced, that is different than another couple of terminology that we sometimes hear in these type of reactions, which is the oxidizing agent and the reducing agent. So when we talk about the oxidizing agent or the reducing agent, the oxidizing agent is the substance that gets reduced, and the reducing agent is the substance that gets oxidized. And that is because they cause the other effect in the other substance. So for example, here, zinc will be oxidized. It's going to lose electrons. When zinc gets losing those electrons, that means somebody else will have to gain them and be reduced. So zinc here, and by the way, it is this zinc over here, is our reducing agent because it's being oxidized. The copper 2 will pick up those electrons. So because the copper 2 needs those electrons, somebody else has to lose electrons to allow that to happen. And that thing has to go through oxidation. So it is the copper 2 here that is our oxidizing agent in this particular case. By the way, the reducing agent, oxidizing agent are always reactants, not products. And you should specify exactly which one you're talking about. So it is clear to me, yes, that I know which one you are talking about. Any questions on that? So again, oxidizing agents or reducing agents is a different question than what is being oxidized and what is being reduced. Okay. Any questions on that? All right. So copper wire reacts with silver nitrate to form silver metal. What is the oxidizing agent? So why don't you write the let's write the reaction there and figure it out. And copper will form a +2 charge on the other end. Yeah, let's take a look. So copper wire reacts with silver nitrate. So copper wire is really just copper by itself. And silver nitrate is our ionic ion. We know that it is aqueous based on solubility rules. So what's going to happen here, it is going to form silver metal. And this is one of those kind of single replacement reactions where the metal will come in and really kick out the metal that is there. And in this case here, copper will gain a +2 charge in this case and make copper 2 nitrate, and our silver will come out by itself. It really is, again, a single replacement reaction that's sort of happening here. Now, if we look at what is happening in this particular case, and we just do our little number line sort of approach, copper on the left-hand side has a 0 oxidation state as it is by itself. The silver nitrate is ionic, which means that is +1, nitrate is -1. The copper over here is copper 2, and our nitrate's -1. And again, the silver by itself will be 0. So anything that is pretty much by itself, not combined with any other element, will always have an oxidation number of 0. So if we just look at the copper in this case, copper is starting on the left-hand side at 0. On the right-hand side is ending as +2, which means it is becoming more positive and it is going through oxidation. In this case, the silver is starting at +1 and on the right-hand side ending at 0, which means it is moving in that direction there and is becoming more negative, which means it is going through reduction in this case. That means in this particular case, the copper, which is going through oxidation, is our reducing agent. And our silver in this case, the silver with a +1 charge, is going through reduction, which means it is actually our oxidizing agent in this particular case. If we were to write our equation here, our total ionic equation would look something like this. Guess I should balance it. That would also be a good idea, probably. There we go. And a 2 there. Now I think I'm balanced. And that will get me 2 of the nitrates. And we'll have 2 of these guys here. That means in this case, it is actually our nitrate that is our spectator ion. If you saw I didn't balance it earlier, I would have had only 1 nitrate on the right-hand side, which told me I did not balance the equation like a bad chemistry instructor. And we will end up with our net ionic equation here. That looks something like this. And as you can see, again, when you do these sort of single replacement reactions or there's redox reactions and you write your total ionic equation, really just 1 spectator ion. And overall, this is our net ionic equation. And we see our copper going from 0 to +2 and our silver going from +1 to 0, basically picking up the 2 electrons that the copper is going to basically be given off, 1 electron per silver ion, basically in this case. Yeah. Any questions on that there? All right, we will stop for now here.